I wanted to start by saying that this work was completed with my advisors, Professors Michael Foss and Petronella Radu, as well as Dr. Mike Parks and Dr. Jeremy Tregesser at Sandia National Labs. And it was supported by this NSF Intern Award. So we know it's really hard to find explicit solutions to PDEs, and it's even harder for nonlinear PDEs. So we look at properties of solutions instead sometimes, including Hadamard-Wellposedness involving uniqueness, existence, and continuous dependence with respect to boundary or initial conditions. And today in this talk, we'll focus on this third one for non-local models, and we'll also extend this definition to include stability with respect to things like the forcing term. For our non-local models, we'll look at the kernel, or sometimes we'll think about different coefficients or parameters that are specific aspects of our models, so on and so forth. So what it means for you to have continuous dependence on data is if we have maybe some operator applied to some solution U, and maybe it produces some forcing term, maybe you have some boundary conditions. If we change any of these conditions, these boundary conditions, forcing, or this operator a little bit, we don't want it to change the solutions a lot. And so mathematically, we'll say we can bound the difference of the solutions above in some norm by maybe some constant, and the difference in the changing data maybe with some different norm. And this isn't just some trivial consequence of uniqueness. So if we think about Laplace's equation in 2D with 0 boundary conditions, and we know that the solution here is 0, and we change one of these boundary conditions slightly. So we're just changing this from 0 to 1 over n sine nx. Well, the solution will be given by 1 over n, e to the negative root n sine nx hyperbolic sine ny. Now, if n gets really big, notice that the boundary condition goes to 0. However, this solution does not, so it'll grow and oscillate rapidly. And so even though your solution, the difference between the solution, or the difference in the boundary conditions was small as n got large, the difference in the solutions goes to infinity. So we don't have continuous dependence even for this linear 2-dimensional problem. So why else do we care about this? Data from experiments is never exact. So if you go out and measure something, there's always going to be maybe some precision error. And we want to make sure that the solutions we've obtained are not going to be largely different from the solution that is the exact solution. Oops, sorry, wrong way. If we have numerical simulations and we approximate data, again, we don't want the numerical solutions to not be approximating the correct exact solutions. Also, if you have randomness or something happening to change your data, you again don't want that to largely change your solution, or you at least want to know how much it's going to change it by. And in the classical case, and we'll use properties of solutions to show this: Gronwall's inequality, Poincaré's inequality, Young's inequality, energy methods, and we can use a lot of these tools when we go about non-local, looking at this non-locally. So let's talk about non-local methods, and if you just watched Haley's talk, we saw some of this already, but back in the 1600s, we started using classical derivatives in mechanics, and we can sort of loosen our restrictions a little bit, and we can utilize weak solutions and have a little bit less differentiability. But if your domain has rough boundaries, or you have some discontinuities in your domain, then even these weak derivatives are no longer going to be helpful. And so then we'll look at non-local models. So instead of considering information at a point like you do with the derivative, we'll think about information around a point. So here, maybe we have some point X, and we can take some information in this blue area called the horizon. Here it's drawn as a ball of radius delta, although it can be other shapes. And we need to do this at any point in the domain, including points near the boundary. So that creates this non-local boundary, or collar gamma, that we now need to take information from. And this has a lot of applications, including image processing, sand piling, and pair dynamics, which is modeling material that has a fracture in it. So for example, here we have a physical experiment where there's a crack propagating, and below is a simulation using paradynamics, which uses these non-local models. And you can see that this angle is actually the same in both the physical experiment and in the simulation. And something you can't see, but is also really helpful to see or to know, is that the speed of propagation is actually the same. So these do a really good job of modeling what we want them to model. So for the rest of the talk, we want to think about if we can find this continuous dependence of the solutions on their forcing, collar, and kernel data. For specific nonlinearities, we want to see if we can also get some continuous dependence results there. We will also look at heterogeneous kernels, and if we have time, we'll talk about extending this results to the nonlocal biharmonic operator. So for most of this talk, we'll talk about the nonlocal Laplacian. So we'll look at a couple of operators. So here we have the nonlocal gradient, which is the difference of u of y minus u of x times this function alpha. And you can think about alpha as sort of recording interactions between x and y. So for example, maybe this is modeling something in like a room. You know, if you are the point y and I'm the point x, maybe you're going to have more of an effect on me if you're close by versus further away. So alpha would weight it so that points close to each other maybe have higher values, and points further away have either lower values or maybe 0 at some distance out. And then we'll also look at the nonlocal Laplacian. So this is that same difference at u of y and u of x times another operator, the kernel mu of xy, integral over the whole domain and collar. And if mu is only supported on maybe some horizon, you can sort of replace this with the horizon. And if alpha is symmetric, and then mu is symmetric, and we can actually write things like the nonlocal divergence of the nonlocal gradient is the nonlocal Laplacian. Although for a lot of our results, we can actually extend these to kernels that are not necessarily symmetric. There are some nice properties that we have, or nice results that we can use. So there's non-local integration by parts. So thinking about moving this non-local Laplacian down to a non-local gradient of u by moving a non-local gradient onto v. There is actually a boundary term, and it's just incorporated into the left-hand side. Non-local Poincare inequality, there's a few different versions of this, but we worked with this one for the sake of numerical results. We can actually get a bound on the Poincare constant when we need it. So we have a few different results. So the first result is a continuous dependence with respect to the forcing term. So we have a non-local Poisson's equation with boundary values or collar values, I guess. And so we're going to change our forcing a little bit, and some amount, and we want to see how it bounds the change in our solutions. And we did get continuous dependence here. So we have this u1 minus u2 is bounded above by this constant that we'll talk about in a second, the difference in the forcings. This is for all p between 1 and infinity. So we have L2p here, so L2 and up. Where here's this constant. And so notice that for this inequality to make sense, we need that this constant is positive, which means we require this restriction. So what this ends up boiling down to in certain kernels, in particular paradynamic kernels, is that your horizon that the points that your kernel is supported on has to be larger than your domain, which is fine because you can just make your collar as large as you want. But it means that you can't necessarily extend these results to, say, continuous dependence with respect to the collar. So we actually have another result specifically in L2 where the difference in the solutions is bounded above by the differences in the forcings again. And actually this constant is just the Poincare constant now. And this follows our usual energy method from the classical case. However, we replace a lot of things with the non-local versions like non-local integration by parts and non-local Poincare inequality. And what's really nice about this result is we actually can extend this result to things like the non-local collar, the non-local boundary condition. So we can get continuous dependence with respect to the collar condition. There is a little bit of a change in the constant here. We include this L2 norm of the kernel, but it's effectively the same result. as well as the continuous dependence with respect to the kernel, where this mu1, mu2 tilde are these normalized kernels, mu1 over the L1 norm of mu1, mu2 over the L1 norm of mu2. And this is for non-local Laplace's equation. You can also get something for Poisson's equation, although for sake of brevity, I've left it out. You create another term to do with the forcing. And you can extend these results also in certain nonlinearities. So here we have a nonlinearity inside the non-local Laplacian. And as long as it satisfies this condition, you can get continuous dependence again with respect to the forcing. As well as Lipschitz condition on the right-hand side. So if you have your Lipschitz, then you can also get continuous dependence there. You do have, again, some sort of constraint happening here because, again, you need this constant to be positive for this to mean anything, which means that you have a bound on your Lipschitz constants with respect to the Poincare constant. So we'll look at a sketch of this proof. So using non-local integration by parts and non-local Poincare's inequality, you can bound this above basically using the same thing, basically using the result from before, that we can bound the difference in the solutions above by the differences in the forcings, although this forcing 2 is with respect to U2, forcing 1 is a function of U1. And then splitting this up using triangle inequality and then using the boundedness of the forcings on this first term, as well as the Lipschitz continuity for the second term, and then using some algebra, you can get that the difference in the solutions is bounded above by that constant that we want, and the difference in the forcings in L infinity. And then we can extend these results to have the same or similar results for heterogeneous kernels. So if we have a kernel that we can split up using the symmetric and asymmetric parts. And we'll define these auxiliary functions. So we have these functions that are L1 norms of mu with respect to x and y respectively. So there's gamma and lambda. And this constant shows up a lot, so we'll define it here. So this is the L infinity norm of effectively the L1 norm of mu to the 1 over p. And then similarly, the L infinity norm with respect to, or of lambda, which is again the L1 norm with respect to y of mu. But this one is to the 1 minus 1 over p. So when p is not necessarily, or when p is not 2, this is actually a different exponent on each of these. So if there's some constraint on this constant, you actually have basically a different constraint on the x and y slices of your kernel. And that will come up here. So here's an example of our results for heterogeneous kernels. So kind of like before, we're just going to look at the continuous dependence with respect to the forcing, although the collar and kernel results also similarly have results like this, where you have this U2 minus U1 and L2 so bounded by some constant, the forcing, the difference in the forcings. However, it's not just the Poincare constant anymore. It's this 1 minus that m that we just talked about times the Poincare constant. So you have now, because you need this constant to be positive, you actually now have a restriction on this capital M. But notice that this is with respect to the asymmetric part of the kernel. So if your kernel is symmetric, this term drops out and we actually have the original result, which is really nice. The proofs for these rely on a generalized version of Young's inequality that we'll talk about in a second, generalized version of non-local integration by parts, which effectively just adds another term to do with the part that is not symmetric of the kernel, and then non-local Poincare's inequality. Oops, my button stuck. I'm sorry. I'm revealing everything fun. So if we want to think about this generalized Young's inequality, so here we have some operator t, that x on v, and we have basically something that looks like a convolution, although mu is not necessarily in a convolution type way. And so we can bound this TV above by that M from before, V and LP. So this is basically a version of Young's inequality that shows up that we can now use for more generalized kernels. So with some of the time remaining, I wanted to talk about some numerical results. So if we wanted to think about, we're going to change the forcing sum and we're going to see how much the solution changes. And we also have numerics in our paper for color and kernel data as well. So here we have everything is going to be set up to be the same except for the forcing. So the kernel is 3 over delta cubed, so that actually you'll get convergence back to the classical solution if your functions are continuous and are at C4. Omega is 0, 1, and our kernel support and ball radius delta, so that means our collar is going to be negative delta 0 with 1 to 1 plus delta. So here's our forcing. So when epsilon is 0, this is actually continuous, and then it's not necessarily continuous once epsilon is larger than 0. And so we'll compare everything back to F0, so when epsilon is 0. So here's the different epsilon values that we're comparing it to. So here's the difference in the forcings, here's the difference in the solutions. And now from this Poincare, or from this kernel, the Poincare constant is actually bounded by 9 over 8. And so this is much less than 9 over 8. So this is giving us the results that we wanted. And here's a graph of the function. So you can see the black is where epsilon is equal to 0, and then the various epsilon values are in these colors. And you can see you are getting some oscillations that you expect. However, they are staying nice and near that original solution. So you're not changing while your solutions are not, changing a lot, even though your forcing is changing quite a bit more. So we wanted to see if we could extend these results to the biharmonic operators. So we know the classical biharmonic operator we can think about as iterating to Laplacians. And there's a lot of nice applications in beam and plate theory, phase separation, and Stokes flow. And there's 2 different ideas in the literature for non-local biharmonic operators. One of them is this finite difference operator. So we have just a single integral here. The second is the similar idea to the classical, just reiterate 2 Laplacians. Here we've shown 2 different Laplacians with 2 different kernels. You could use the same kernel if you wanted to, but just to try to keep it as many different options as possible. So we can actually, for the hinged boundary value problem, we can think about some nice continuous dependence results that are not necessarily immediate, but pretty close to immediate corollaries of the non-local Laplacian results that we just talked about. So here's the non-local boundary hinged boundary condition value problem. So here we have non-local biharmonic applied to U is equal to some forcing. And then in this first collar that we'll show in a second, the picture, we'll have the non-local Laplacian of U is G, U is H in the second collar. So here's the domain, here's the first collar, and here's the second collar. And we can sort of, like I said, extrapolate our results from before using basically breaking this down into a coupled problem. So we can get the difference in the solutions is bounded above by the difference in the forcings, as well as both collar conditions. So here's with the second collar condition, and here's a very similar constant to before. And then here's with this second, or with this first collar condition, you have a little bit of a different constant for this collar, but. And also we can get something for the kernels, the continuous dependence with respect to the kernels. So right now we're working on the continuous dependence with respect to, or for the clamp conditions. And then we're also looking right now at the asymptotic compatibility for the non-local biharmonic for the iterated Laplacians, non-local Laplacians. So that is all I have. Thank you.